not working.
Okay.
Yeah, we'll figure it out. So please, Professor. Yes, thank you.
Okay. Good morning, everybody. I already forgot my badge. Although I'm on Sanpera, just in case you drank a lot yesterday evening or you didn't work out here. Yesterday was warming up, today is not warming up. So I hope you are in conditions to follow. Okay, so what did we do yesterday? We did just two things, okay, that many of you know. First of all, we defined what is a composite, pure quantum state, and we say that it's in a product state or separable, it doesn't matter, it means the same. If it can be written as a tensorial product of states, each of these states, psi I lives in a hyperspace, and psi, the big psi, lives in the composite system of the hyperspace. Otherwise, we say if we cannot write my state, I cannot write it like that, I will say it's entangled, so that was lesson 1, okay, 1-0, and the lesson 1-1 was that given a bipartite pure state, psi of AB, okay, the first definition doesn't matter if it's bipartite, multipartite, it's the definition of being in a product state or being entangled. Well, the second one is only for bipartite systems, and we say any pure state in a bipartite system, I can write it in a special form which is called the Schmidt decomposition, okay, in which I say it's very important that you see that in this Schmidt decomposition, okay, you just have one index I, not I. And I have two orthogonal bases, one for Alice, one for Bob. And then I said that when I write my bipartite pure state like that, I have all the information about the entanglement, content of the state. So, and then we started to introduce, and I will go back here, what is a mixed state. And we say that a mixed state is an ensemble of pure states, and it describes a situation in which I know with some probability that my physical system is described by the state or the vector psi. Okay? And then when I write this like that, I say rho. Okay, this is what it's called, and we will say it. Okay? Rho can be written. Yes, of course, because I'm seeing my transparencies at the same time, so I'm also a little bit stiff. Okay, so I say, with this we saw it also yesterday, and we stopped more or less here. And we say I can write my density matrix as a convex combination, we will call it like that. This is the mathematical term, because these are positive coefficients, we will sit here, they have to sum the identity, because a density matrix has to have trace 1, and it will be written like that. Okay, and so about these mixed states, always, these are real numbers smaller or equal than the 1. Normally, we can say that we have an ensemble of pure states, we can write it like that. These two, in this direction, is the same. So I have some probabilities of being in the state psi, so I have a density matrix. Okay, and I say that since all the coefficients are positive and the sum, the identity, this is a convex combination of projectors, because this is a projector on pure states. And now the funny thing is that, of course, if I have this ensemble, I have a density matrix, but the other way around, it's not like that. So that means that a density matrix can be associated with many different ensembles, and that makes the things complicated, okay? And we will see why it's like that. Okay, so in this direction it's clear, but in this direction there are many different ensembles that they have the same density matrix. Okay, so, and then we say, okay, it's the best thing, it's to rephrase the postulates in the density matrix formalists, because it includes the pure states, and we were doing that yesterday. Okay, so we say the system is always described by, what's here? My system is always described by an operator, it's a matrix, okay? This means operators that act on a hyperspace, this is how we read it, okay? And they have to be defined positive, so if I diagonalize my matrix, these are the eigenvalues, it's Hermitian, because it's positive, but on top of that they have to be positive, okay? So a Hamiltonian is Hermitian, but it's not defined positive. So if it's positive, it's Hermitian, if it's Hermitian, it doesn't have to be defined positive. And the trace has to be equal to 1 because we normalize all the states. And then we say that the evolution now, instead of being just an operator acting on a state, it's going to be a map, I will call it like that transform density matrices into density matrices. And these maps, okay, is sometimes I write it like lambda, sometimes I will write it like this big E. Okay, normally it's a map that depends on the time, if I have an evolution. And this map has to be positive, completely positive, I will explain what it is later, and trace preserving in general. So that if I have a system and something happens, at the end I have to have a system. This is what it needs to be trace preserving. Okay? What it cannot be is trace increasing. I have a particle, something happens and I have two particles, that cannot be. Okay? Unless I have a decomposition, that doesn't matter. In particle physics I can have that, but it's the full thing. And what else? And then I say that postulate 4, which is the postulate that we are going to be more interested, is the same. Okay? In the matrix form formalism, I say I have now a density matrix which belongs to the space of bounded operators in this composite Hilbert space, and now I define that the state is separable, okay, if I can write it as a product state of density matrices. Okay, so how is the world according to quantum information theory? Okay, so the world according to quantum information theory, it will be like that. Okay, so it's pretty beautiful. Okay, so I have a set which I would say it's convex. Okay, an egg, but this is also convex. So convex is that I don't have a hole in between. No? So I cannot have something like that, and we will see why. So this is a set which is convex, and this is a set which is not convex. So what it means to be convex is that any two states, okay, the line that it joins any two states has to be included in the set. So this is clearly not convex because this line is outside of the set. So quantum world is like that, and it's very nice that it's convex. Okay? And then there are extremal points in this convex set. So for instance, the extremal points in this set that I'm writing here is everything which is in the order. Okay? So that it's compact indeed. Okay? So it's convex, and the boundary belongs to the set. So these are the extremal points. So, but if I write a polytope, which is also so this kind of form, okay, what do I see is that the extremal points in this set of quantum states, they have to be projectors on pure states. And these are these red points that I put here. Okay, so if I have these 1, 2, 3, they will correspond, they are extremal. The extremal points of the convex set are the points that I cannot write as a convex combination of other points of the set. So these are these ones. And then I can have also in the border, so in the surface or in the facets of this polytope, for instance in this one, I can have mixed states which are rank deficient. Because in this triangle that I wrote here, okay, whatever I have a convex combination, for instance, this point of here, which is with probability P1, I have this guy, with probability P2, I have this guy, with probability P3, I have this guy. And if I am in this facet, okay, then I have a density matrix which is rank deficient. Okay, so, because obviously, what is the dimension of this guy? Larger than that. Okay, so I can think that extremal points are projectors of pure states. In the facets, which is the external point also, I have density matrices which are rank deficient, and then inside of this polytope, I will have any state which is inside of this polytope will be a convex combination of the extremal points. So I will have the density matrices. So I can write it like that, okay? And then we will see. This is in general, doesn't matter if I have a composite system or a simple system. Okay, so I say that quantum information tells us that the world is a convex set, which is very nice. Okay, but now if we want to talk about composite systems, what happens the same, and then we'll say, okay, composite systems in quantum information will be also convex sets and convex polytopes. And I will define in a very general way. Correlations, what is a correlation in a composite system? Even a classical correlation, I can define it like that. I will say that a correlation, even a classical one, that, for instance, I measure X in my system, I measure Y. So Alice measures X, Bob measures Y, Alice obtains A, and Bob obtains B. If this is not equal to the probability that Alice measures X and gets A, and Bob measures B and gets Y, if this is not equal, this is a correlation. And classical correlations are the same. Okay, so we are classically correlated because we are now here. So I'm talking to you, some of you are listening. So there is a correlation, okay, but this is not. But quantum correlations is the same, okay, a little bit more complex. So if we want to see how is the world according to quantum information, then it's like that. As far as we know nowadays, or as far as I know nowadays, maybe I'm already not updated, but I think it's like that. So there is three kinds of things that we're going to say. We have non-signaling, okay, these correlations which are non-signaling. I don't want to enter, it's the bigger one. So what happens if we can have non-signaling, which is what happens. I think so. Nothing can go faster than light, so it cannot be non-signaling. Then we have, but I will not talk about that. Then we have local correlations, and local correlations, they can be explained like following. So the probability that Alice gets A and Bob gets B, assuming that Alice has measured X and Bob has measured Y, okay, depends on a parameter lambda, which is normally called a local parameter or hidden parameter and so on. These are classical correlators. Okay? And they are called local. And then there is the quantum correlations. Quantum correlations are given by the Born rule. There is nothing else. Okay? So, which is that? This corresponds to the trace that this is Born rule. Postulate 3 of quantum mechanics. Measurements. I have a density matrix AB. Okay? And I apply measurement X whose outcome is A. On Bob applies measurement B with outcomes is Y. And this, the world is like that. Okay? So the three things are either a convex set or a convex polytope. The non-signaling is a convex polytope. A convex polytope means that the number of extremal points is finite. Okay? A convex set is a convex polytope with infinite number of extremal points. And this is the reason that I write it like if it was an X. Okay? That it has infinite many extremal points. And the local points is also a convex polytope. Very big. It depends on the dimension. So we know that it's on this form. And now, what distinguishes a local polytope from here? Okay, what distinguishes these local correlations from quantum? Well, this is what we call a Bell inequality. Okay? A Bell inequality is this thing of here. It's a plane, okay, which separates local from quantum. And now I want to look at the quantum, because we are going to talk about entanglement and quantum, and I say, okay, this is a convex set, this one, this blue, okay, whose extremal points are projectors on pure states or rank diffusion density matrix. And inside, what do I have? I have density matrix, which are operators, which are on this way, and which are formed as a convex combination of PIs, CIs. Inside of my convex polytope, of course, I can have density matrices which are rank deficient. So when I diagonalize my matrix, I have zeros. This is what it means, rank deficient. But I can also have rank deficient in the extremals, because as I told you, the polytope, if you have a facet, and I don't know how is this thing, I can have rank deficient there. And that's it. So if you know that, you know everything. Okay? So, and then what do we have to do? Well, now, since we know all these things of here, what we would like to do, it's the following, okay? It's, why I started like that? It's a little bit strange that first I talk about mixed states. Well, I want to define what is entanglement, okay? Or separability in mixed states in a more formal way. And I say, okay, a bipartite, and of course, multipartite will be more complex, but these definitions are the same, and you will do it today without Fred. But a bipartite, rho AB, Alice and Bob, I say is separable if it can be written as a convex combination of product of density matrices. And now, why I write these two things with different letters? Well, because I know that each density matrix, it can be written as the convex combination of projectors on pure states, EI for Alice. And the same for Bob. Therefore, if I join all the parameters, okay, this will be a different value, because I will have decompose this guy, I will have decompose this guy in product states, and I will write it like that. Where PIs are all positives, and the sum identity, and QIs, of course, if I write it like that, are positive, and the sum identity. So, in other words, we will say that a state is separable if, and only if, I can write it as a convex combination of projectors on product states. Or if you want, I can write it as a convex combination of projectors on local states. Okay? So, what does it mean to be separable? I want to put this remark. It means that my state can be prepared. So how do I understand a state like that? I understand a state like that in the following way. Okay, so we have two parties, Bob and Alice. Okay, and there is a kind of God who says, you Alice, with probability P1, okay, you prepare rho EI, and you Bob, with this probability, you prepare rho EB. Okay, now with probability P2, you prepare that and you prepare that. With probability P3, you prepare that and you prepare that. So this can be done local. Okay, there is somebody who is giving us these instructions. Okay, so this is what it means. So to be separable means that the state can be prepared by local operations and classical communication, because I need this classical communication. Okay, I have to say, you prepare with this probability this, okay, or I am Alice, I say I'm going to prepare with probability 1/2 my state, and I call Bob with a telephone, and then I say, okay, you prepare this state probably, and so on and so forth. So now, we know everything, now we have to say, okay? So, let's go back, because now we know the definition, so, and now I can say an extra definition. So, entanglement for bipartite pure states, and for all pure states, okay, and this is something that not so many people is conscious about, that means the following, okay? So, these two things that we have seen, that means the following, that we say it's entangled if it cannot be written as a product state, obviously. It's entanglement if it's entangled if I write it in the Schmidt decomposition and the rank is strictly larger than 1, because if it's 1, it's like a product state, or it's entangled if my state violates a Bell inequality. If it's pure state, this is exactly the same. These are 3 definitions of entanglement. But this one, as you see, it's a little bit different and has much more substance on it. Okay, so now we start the lecture 2. So that was the warming up. And now what we are going to do today. So today I would like to say, well, we have defined what is entanglement, but how much entanglement it is. Because this is a resource, so you have to be able to tell me how much entanglement you need, and I can say that if my resource, my quantum state, has this entanglement so that you can do this task for me. So for instance, yesterday we put an example of superdense coding in which we say, I'm able to transmit, just sending a qubit, 2 bits of classical information. But what is the catch-up? That I have to have a resource, which is entanglement. So between the 2 people that they want to transmit us using only once the channel, so you have a telephone, which is my telephone, for instance, it's from Spain, and I don't have an eSIM, and I have to use it only once, okay, to say I'm here. I don't want to use it often, all right, so I can do it. But only once, this is the thing. Of course, if you have a channel which is free, maybe this is not the most important thing. But you have to know the resource and how much do you need to do that. So we have to define that. And how we are going to define it? In the following way. Blah, blah, blah. Okay. So let's put the states like that. I say this is convex set, and the first thing that I want to show you is on the set of the quantum states, now I can write another difference. Okay, I can say I have a subset of my states which are separable, and this subset is convex. Okay, which it means the following, and it has the whole sense. If I have a system which is separable, and I have another system which is separable, and I sum these 2 systems, well, this is separable, because I'm able to prepare it locally, okay, so it's not a problem. So this set, it's nice because it's convex. And whatever is not separable, we say it's entangled. But the set of entanglement is not convex, okay? Because the set of entanglement makes like that, has a hole here. Okay? And to characterize something which is not convex is very difficult, super difficult. Okay? So this is more or less what we have to do. And so, this is the way that we can see it like that. Okay, so first of all, why I told you that for a density matrix there are infinite many decompositions. Well, you can see it like that in this example. No, I have my composite system, rho AB, and of course this guy here I can write it like the superposition of these two guys. Okay, a convex combination of these extremal guys, because this is the line that joins these 2 points, but also as a convex combination of these 2 points, and as a convex combination of these 2 points, and so on and so forth. So there are infinite many combinations. And this sounds nice, but it's not so nice, because which is the best, okay, superposition I can do in order to get. And this is some of the things that we will have to do. Second thing that happens, that is very curious, is the following. So, why separable states? I don't know if I have given the right transparency. Why I say that? Okay, because this is what I was saying. If I have a state which is separable, so it's in this set, and I have another state which is separable, it's in this set. Okay, so let's say I have this guy, P1, rho 1, rho 1, and rho A tilde, which is another convex combination of other states. And now I add them as a convex combination with probabilities that they sum the identity, because if not, I will not have a state. Well, what I'm doing is just joining these 2 lines. So I'm looking at all the states which are in between these 2 points. And since the separable set is convex, any line between 2 convex sets is separable. But now imagine that I want to do the same with 2 entangled states. So I have my entangled state, this one, and this other one. And now I do the convex combination all of them. And what happens? Well, it can happen that a convex combination of 2 states which are separable are entangled. How can that be? Okay. This is very surprising, not a priori, because I say, well, if it's separable, it's obvious. Because I have prepared it separable, okay? Local operations, I can do it. But now I'm saying something different. I have a state which is entangled, you have a state which is entangled, we mix our states, and the result is a state which is separable. So the correlations, the quantum correlations have washed away. Why is this so? Well, this happens because in a mixed state, obviously, in a mixed state, there are correlations. So you see it here, no? Here I have correlations. Some of the correlations are classical, and some of the correlations can be quantum. So I have correlations here, because if I measure rho E of 1 or rho E of B, I will have probability P1. So these guys are correlated, but this is a classical correlation. So the mixing of classical correlations with quantum correlations sometimes washes out the quantum correlation, and that makes this problem very difficult. So what else? So now I have a state that somebody tells me that it's entangled. Okay, it's a density matrix, so for the moment, and I want to say, okay, how much entangled is that? So I have to have a measure, okay, because how tall I am, I need a meter, so how much entanglement, I need a measure. So I have to define what is a measure of entanglement, and we will go here. So what is a reasonable measure of entanglement? Okay, so what we have to ask for a measurement to be a measurement? Well, we have to ask the following. First of all, that this measurement of entanglement, that I'm going to call it E, capital E, okay, has to be positive or equal than 0 for any state that I have. Okay? It cannot be negative, because it's like to say, how tall are you minus 3 meters? Doesn't have sense, okay? So I cannot be like that. So I will ask that this measure is positive. Then I will ask that this measure is 0 if, and only if, my state can be written in this way, okay? So it has to be 0 on all the states that they are separable, and this also has a lot of sense, no? So I want a measurement that measures whatever is entanglement. So it has to be 0 in everything which is entanglement. Then somebody was asking yesterday this in front of local unitaries. Was somebody hitting this? So the entanglement cannot increase, but can remain the same. And I was saying, yes, imagine that I make a unitary, which is trivial identity on Alice and Bob. Okay? So on average, if I'm Alice, you are Bob, we are in the lab and we are manipulating, the entanglement definitely cannot increase because we are doing things locally, but it can decrease. Okay? So for instance, I have a single, I measure my part and the entanglement is lost. Okay? So this has sense. Then, given local operation plus classical communication map, so if this is the map, this is exactly, it's the extension, not only to unitaries, it's the extension of that. The entanglement, once I have applied this local operation, cannot increase. Okay, it has to be like that. And then there are other things that I can ask, but they are not compulsory to be measured. It would be very nice if it fits that, but it's not necessary. First, it's convexity. That I can say that, okay, the entanglement of my state has to be smaller or equal than the convex combination of the entanglement of each of the realizations of my state. This is what it's called convexity. And then I can also ask for additivity. So if I have n copies, okay, so my total state is rho to the n, it would be very nice that the entanglement of rho to the n is n times my entanglement of one copy. So if I have 10 coins of, or 10 notes of Brazilian things, I would expect that if I have 10 notes, so 100, I don't know, Brazilian reals, it will be 100. But it doesn't have to be like that. So sometimes you can have that additivity doesn't happen. It's not required to be a measure. It's nice, but it's not required. So, and what happens is that there are many different measurements that they are equivalent. And this is what I would like to go today for that. Okay? So I will start by defining a measure which is very fundamental, and then some of them which are not fundamental, but I would like that you listen to them in order to understand why we use this measure. So normally, if we have a pure state, okay, and now I'm going to talk about pure states first, okay, I will say bipartite. The entanglement measure that I would like to use is the entanglement entropy. Okay, so given a bipartite state, psi of AB, the entanglement entropy is the von Neumann entropy of the reduced density matrices. Okay, where the reduced density matrix, you know what it is because we saw it yesterday. We have to trace out one of the systems, and S of rho is minus trace of rho log of rho. Okay, how do you do that? So density matrix, of course, what is the log of a density matrix? You always do it like that. You have your density matrix, you diagonalize, and then the log of your density matrix is the log of the eigenvalues, okay, which are positive, so everything is fine. And the trace is you sum rho log of rho. You have your matrix diagonal, so you can do that. Okay, so this is what I say that the rho EB are reduced density matrix, normally also called marginals. So I have a bipartite system, and I only look at my Alice, I discard Bob, this is called the marginal, define it like that. Why this is the measure? So everybody uses this measure for bipartite systems, and it's a very good measure. Why? It's easy to calculate, and it has a lot of sense. But why? Where does it come from? Okay, and this is what I would like to discuss today. This can be used for anything that is bipartite. So for instance, it's used very often to describe a condensed matter system in which I have a quantum phase transition. So imagine that I have an Ising model in which I have two phases, all right? In this Ising model, normally ferromagnetic, because I put a magnetic field, so I have, I don't know, 1 million spin, 1/2 particles, and when I put a magnetic field, they all are oriented along this magnetic field, so this is ferromagnetic. And when I take out this magnetic field, because they have interactions, sigma, okay, so this is a model which is, you all at some moment hear it. So, for instance, something like that I have a model, it's like that. Too many things. I have a Hamiltonian. Okay, it's not, I write it like that, minus the sum over e plus 1 next neighbors, sigma I of x, sigma I plus 1 of x, plus a magnetic field sum over sigma IZ. Okay, so, and I goes from 1 to n. So I have this Hamiltonian, and I have to put here a term j. Okay? And this Hamiltonian tells me that if I don't have anything here, okay, these guys, they are oriented along the x-axis, okay, so they are interacting. If I have a magnetic field along the z direction, and this magnetic field is big, of course, all the spins, they will go like that. And if h over j goes to 1, okay, the spins, they don't know what to do. Okay, they say, okay, what do I have to do? I have to be oriented along the z direction because I have a magnetic field like that, or I have to be oriented along the x direction because the interactions, okay, tells me that I am minimizing the energy if I am oriented in the same direction. So this is a quantum phase transition, there's nothing else. Okay, so there is a moment that the system, the physical system, is confused and doesn't know what to do, and then you have a phase transition. Okay, so this quantum phase transition, you see it with the entanglement entropy. You see it. Okay, so you have your state, and you cut your state into parts. You have 1 million spins, doesn't matter. You take 500,000 and 500,000. And then you see what is the entanglement entropy as you go to this limit. Okay? When you go to the phase. And then you see that the entanglement entropy, bam, has a peak. Okay? So just when you have a quantum phase transition, all the spins, just at this moment, they are entangled, highly entangled. Okay? In other conditions, when they are ferromagnetic, they are not entangled. This is a product state. It's the definition of a product state. So entanglement entropy is super useful, okay? But why it's this expression of here, okay? And this is what I would like to spend a little bit. So there are 2 measures of entanglement which are conceptually very important, but very bad for using it. So you shouldn't use it. But are the ones that they tell us why this entanglement entropy they are, okay? And what I say is that this entanglement entropy, this one you have to know it. If you are going to use entanglement in pure states, you have to use entanglement entropy. Okay. So let me say a little bit more about this entanglement entropy. It's a good measure, yes, it's a good measure because listen, what does it does? Okay? So if I have a state which is a product state, okay, the entanglement entropy is 0, and we can see it very fast because if I have a pure state and I write it, it's already the Schmidt decomposition, it has only one coefficient and lambda, okay, the diagonalization is equal to 1, log of 1, 0. Okay, so it's a good measure. If I have my pure state and I write it, and this is how I should do it, in my Schmidt decomposition, so this is diagonal, orthonormal basis, in this way, in the Schmidt decomposition, and now I calculate which is the entanglement entropy. This is minus lambda I log of lambda I, which is the Shannon entropy. Okay, so it's fantastic. When is that big? This is big. When is that big? So log or x log of x is a function that it makes something like that. Okay, so when x is 0 is 0. When x is 1, log of 1 is 0. So it's very big. When x is around 1/2, so maximally entangled state. It's a good measure. We will call, okay, when we have this state which is 0, 1, minus 1, 0, this is the singlet, and then I calculate which is the entanglement entropy, and this is 1 e bit. We will call it this is our point of entanglement, okay, 1 quantum bit or entanglement bit, and it's a singlet. A note of remark, this is the Schmidt decomposition, but there is a minus here. So I say on the Schmidt decomposition, all these lambdas are positive. This doesn't matter, because this minus, when you find something like that, you put it inside. You put plus, minus, okay? And you have to put it as a phase. So if you have a maximally entangled state in any dimension, this is for qubits, okay? In any dimension, I say that it will be of this form, 1 square root of d, okay, if I have a bipartite state of dimension T, I. And then my entanglement, okay, of the singlet or the maximal entangled state will be log of 2 of the dimension T. And what I say, if I have many parties, and this you will see today, you can always scatter and calculate entanglement entropy. So it's fantastic. Why this? Where does it come from? Okay? So indeed, one can say, okay, if I have, first of all, what happens if I want to go to mixed states? And then we will go back, why this entanglement entropy? If I want to do that for mixed states, you can say, okay, what is the best thing to do? This is what we call convex roof extension. So if I know that mixed state, it's a convex superposition or combination of pure states, and I know how to calculate the entanglement of a pure state, I would say, well, I know how to calculate the entanglement of the density matrix, no? I will just do a roof extension. So I will say that the entanglement, okay, I will do something like that, okay? I will say yes, the entanglement of my mixed state will be, okay, pi, the entanglement of all these states which form my mixed state. Okay, this is a convex roof extension. But what happens? That for a density matrix there are many different decompositions. And have all the compositions give the same entanglement? No. Okay? So here we have a problem. So, which is the entanglement that this state has? Well, I have to look for all possible decompositions, okay, of my density matrix, of possible decompositions, and minimize, okay? So I minimize of all possible decompositions, and I say, okay, this is the entanglement of this content, okay? Well, this is super difficult to do, okay, because there are many things. So this infimum, and this will define, okay, the entanglement of formation. So, what is the meaning of this thing? Well, if I'm able to do that, okay, it will tell me, I can understand it like that. It gives me, on average, which is the entanglement that I need to form this state. But the problem of this measure, okay, which I will write it like that, it's that a convex roof optimization, and I think Otrid will work, I will talk and explain much better on these things, is very hard. Okay, so only for 2 qubits, no, bipartite and 2 qubits, I can do it. Okay, and for these 2 qubits, it's something called the concurrence. I don't want to go to the formulas because imagine, I found it boring, imagine you, which are sitting here, okay? But what I want is that, so you will have the notes and so on, you will see. What I want to say is the meaning, okay? So, the concurrence is a measure that allows us to find which is the entanglement of formation of a mixed state which is formed by 2 qubits. And it's a closed formula, you can calculate it, okay? That's fantastic, because if you have this entanglement of formation, you are done. And you can do it, you do it, and so on. Okay? It's, you have to have this basis, I don't care. Okay? It's not interesting. All this, also it's not interesting, except for the following. Okay? So I can say, well, I can give you the concurrence of a state, it's blah, 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 blah. We don't worry, it's something, okay? But what is important is here. It's the entanglement of formation, which tells me on average how many entanglement I need to create my state, which is this thing, entanglement of formation, it's related to the concurrence, okay? So if I know the concurrence, I know the entanglement of formation. So I have this meaning that I say, okay, I want to calculate, I give you a state, okay? A mixed state of 2 qubits, whatever it is, a density matrix, and I say, it's entangled. First of all, what do? You calculate the Schmidt decomposition. You say, oh, it has 2 Schmidt because its dimension small. I have maximum Schmidt rank can be 2. Yes, it's entanglement. How much entanglement it is? You say, okay, I calculate the concurrence and you give me this number. That's fine. This is a good measure. It fits everything, I don't need to know anymore. But that only happens for qubits. Okay? So now, in general, what do we have to do? Okay? In general, I want to talk about 2 other measures that they are not useful, but they are very useful to understand what is entanglement. And this is entanglement cost and entanglement distillation. And these 2 measures, they are in some way, okay? Entanglement cost and entanglement of distillation, this is in some way two dual measurements of entanglement, which they work for qubits and they work in the following way. So I ask myself, which this is a very meaningful question, how many singlets, which is my unit, my money, do I need to prepare a bipartite entangled state ROE? Okay, how many do I need? Okay? So maybe I will need on average half, or on average one, or I don't know, no more. Okay? And now I can do the same question the other way around. I give you a density matrix, and we always have to think that quantum mechanics is a probabilistic theory, so you have many copies. So I give you 1,000 copies of my state rho AB. I give it to you, and I say, how many singlets from here you can distill, okay? There is a protocol called distillation, so you can end up having singlets, or maximally entangled states. How many you can have? Okay, so these two have a lot of sense, no? Because in some ways, how many do you need? Okay, how much do you have to pay in order to have your state? How much from your state you can extract? Okay, entanglement of cost, entanglement of distillation. All these things, they have to be thought in the asymptotic limit. And now you will see why this, which has a lot of sense, is very difficult to do. Because now I'm going to define it properly in order that we understand what it is. Okay, so we say the entanglement cost, okay, of a mixed state, it's the infimum, okay, the smaller, over all sequences of LOCC protocols such that given n copies of a singlet, so I have a singlet and I have n copies of this singlet, okay? Now, I do all the protocols that I can imagine, okay? And I choose the infimum such that all these n copies of my singlet goes to this state sigma, in such a way that the distance of my state, n copies of my state, and sigma, when n goes to infinite, goes to 0. Wow. And this is a proper distance, okay? It has sense, all right? So it's telling me how many singlets asymptotically I need to create my n copies of my state, okay? And I have to do it in the asymptotic limit. And I can write it like that. It's like the rate, okay? This is a rate, okay? On how many singlets, assuming that I have n singlets, okay? And I will extract n states of mine using all these things. And I can also think that this entanglement cost is the limit of the entanglement formation in the limit that n goes to infinite. So, doesn't matter, these are formulas, but in simple words, what we are saying is how many e-bytes one needs to create an entangled state rho, which is the closest possible to the one that we could achieve if we have n copies of our state using only local operations and classical communication. As you can imagine, when you see all these things, okay, minimize overall possible LCC and then take the limits and all that, this is super difficult. But it has sense, no? I think this is the same. And now I want to define the entanglement of distillation. So how am I going to do the entanglement of destination? The entanglement cost is the minimum number of singlets that I need in order to get my state in the asymptotic limit. The entanglement of distillation, it has to be the maximum number of singlets that I can distill from my state, because I want to distill as maximum possible, no? So this is the supreme of all LOCCs that I can do in order that and I get singlets. Okay, so I'm changing the roles. That's it. And I can define it like that. It doesn't matter. So it's only how many singlets I have to put in order to get my state, how many singlets from my state I can extract. And okay, so and now the things which are important come here. Okay, which is first of all, it has the whole sense. The entanglement of distillation has to be smaller or equal than the cost, because it cannot be that I create my state and I put 2 euros, I have my state, and I extract 5 euros for it. It doesn't happen In quantum, it doesn't happen either, okay? So if I need two singlets in order to create my system, from my system I cannot extract more than two singlets. If not, it would be fantastic, but it's not the case. So to create is always bigger than to distill, okay? Second theorem, which is important, any other entanglement measure has to be in between these two ones. Cannot be an entanglement measure, and this is why physically these measures are very important to understand, okay? So any entanglement that I can imagine, I can create, I can invent, there are thousands of entanglements, they have to be between the entanglement cost and the entanglement of distillation. And for pure states, and only for pure states, there is one entanglement measure which is exactly the same as entanglement cost and entanglement of distillation, which is entanglement entropy. And this is why we use entanglement entropy. Okay, so this is the measure for pure states, bipartite, and coincides, and only here coincides. Okay, so any other measure, the entanglement measures, they don't have to coincide, they don't have to have the same character, they don't have to grow equal and so on, they can be very different. But we have that for pure states, the entanglement entropy is the one which coincides with entanglement of formation, of cost, and entanglement of distillation, and this is why we use it. Wow, we are almost done. Yes? So what happens, this is only for qubits, okay? Well, no, but what happens if I have higher dimensions? Okay, so if I have two bipartite systems, but it's not qubits. I cannot do this Schmidt decomposition. Yes, I can do it, sorry, right? If I go to higher dimensions, okay, what I'm going to do? Then I'm going to calculate something which is called the negativity. Okay, I want to measure now, okay? And I will call the negativity. And the negativity, it's important, but I think we probably will also look at that. It's the following, okay? It looks very strange, but it's not strange, you will see. I have my density matrix, rho of AB. I will partial transpose this density matrix. I will explain tomorrow why it's the physical meaning of that. I will extract the identity and divide it by 2, and this is the norm, okay, of an operator, trace norm, which is you take the trace of rho, dagger rho. Okay? What is this partial transposition? This partial transposition is, I have my density matrix, it's a matrix of a composite system, this is Alice, this is Pop, and now I change files and columns in only one of the systems. So for instance, in Alice, okay, I have changed files, now it was I, so it's J, it's I, Y, Bob, I don't touch it. Okay. It has a lot of sense, and I will explain you what physically it means. Okay, so, but now we just take it like that. And when I do the partial transposition, if the state, some of states which are entangled, they have negative eigenvalues on this thing, and then I go back and I say, okay, I look which is, okay, the absolute sum of the negative eigenvalues, and that it's a very good measure of entanglement. We will go back to that, and I want to finish with these two measures, which are completely different, okay, and which have a geometrical sense. So until now, I was talking not at all about geometry of the system, but I can do the following. So, okay, if quantum world is like that, and it's like that, because I told you this is like that, okay. If this is like that, okay, so this is the density matrix. So I know that there is separable states. I know that they are entangled states. I know that in the separable states there is the identity, because the identity is separable. So why an entangled state is so fragile? Because when I add noise to this entangled state, it becomes separable. Okay? So a good measure of entanglement, this is from Vidal and Bernard, okay, it's to say the following: how much separable state I have to add to my entangled state so that it becomes separable. Okay, so the robustness of a quantum state, it's the minimum state sigma which belongs to the separable. Okay, can be the identity, can be other thing, and a parameter S such that my state plus S times this separable state, and I normalize it so that trace is 1, becomes separable. So how much I have to add here so that my state becomes separable? This is a very good measure of entanglement. It's a fantastic measure of entanglement. it's not very easy, because sometimes it's very difficult to know if a state, and I will explain you why it's not easy, but geometrically it has a lot of sense. There is another measure of entanglement, which is the best separable approximation, which is very similar, but it's not the same, which says, okay, if I want to know how entangled is a state, maybe what I have to do is to look which is the closest separable state, which is here. And these two measures, normally they don't coincide. So I say, if I have a state, rho AP, I can always write, for qubit is always like that, like a separable state, lambda times convex combination of a separable state, 1 minus lambda unentangled state. And I ask if lambda is a good measure of entanglement, okay? Yes, okay? If lambda is 1, the entanglement is 0. If lambda is 0, the entanglement is 1, because this will be a singlet, okay? And in between, this is a good measure of entanglement. So these two measurements are not like entanglement entropy, which is very easy, but there is a theorem which shows that any other entanglement measure is in between these two measurements also. Okay, so these are two external measurements. So I think that I will like to finish here. It is a little bit early, but if you want to, I don't want to enter to the next topic. I think it's already quite dense for this morning session after yesterday, so I will stop here if that's okay for you. Thank you very much.
Thank you, Professor. Any questions? Just a second. Thank you very much for your talk. So when you're talking about the definition of an EBIT and about entanglement, distillation and cost, you're always talking about the single state. Is this convention, or because the other L states are also maximum entanglement, right?
Maximum entanglement. We call it singlets because singlets. Because they are different from the triplets, but it's exactly the same. All of them, this is the Bell basis, or it's the same. Psi minus, psi plus, any of the states are the same, yes. Are the same, one EBIT of entanglement.
Thank you.
It's just conventional.
Well, thank you so much for this very enlightening lecture. Can you give a bit of an intuition of why they're not the same and why?
Okay, because if I put it like that, it looks, no? Because I have made this drawing, so it looks like if I trace, this will be the closest place that I will enter. But this is not like that. Okay, so maybe I have, so these two things are, first of all, I just for qubits here, I will put a very easy demonstration of why it's like that graphically, okay? So the fact, I say that on the border of a very easy one will be like that, okay? But one has to be a little bit careful with these things. So I say that on the border of my quantum states, I will have the pure states and rank the fission. But here, well, this is not a border, okay? So a priori, I don't have a pure state here. So when I enter here, okay? When I enter in this direction, okay? I'm getting this lambda s, but I'm not putting with an entangled state. Well, when I write it here, I'm making a convex combination of one of the extremal points, that it has to be here, plus something which is here. So this gives you already an intuition that these two things, they don't have to be the same. Okay? The robustness is very nice because this is what physically happens in the lab. Okay? So you prepare a state and you have noise. And if the noise is white, this is the identity, which means all kinds of noises. And this is the reason that I didn't put it here, like a white noise. It doesn't need to be white noise. Maybe it's a separable state which is not white noise. But this is exactly what happens in the lab. And this is why entangled states are so fragile. It's like that. They become very easily you disentangle them. There are many other measures. There are many other measures of entanglement. Many. You can invent one. Okay, it has to fulfill these 4 requisites. You can invent one. Maybe you invent one, which is very good. I think it will be between these two, but because this is proof, and it will be between for sure the separable and parallel.
Hi, thank you for doing that. So, can you give some intuition or some comments on why qubits are so different?
Sorry?
Why qubits are so different? Qubits, like when we have to...
Why qubits are different from higher dimensions? Let me think why they are so different from higher dimensions. Well, first of all, I think that because, for instance, in this entanglement cost and entanglement distillation, okay, and formation, you always think on your resource as a qubit, okay? And you can calculate it like that. Are super difficult measures to do. So this is what I'm telling. Nobody will use this entanglement formation, entanglement distillation. But your qubit, this is the simplest system that you have. So, of course, you probably can do the same and say, okay, what is the maximal entangled state if I have two spin-1 particles? Okay? Yes, I know it would be 1 square root of 3, 0, 0, plus 1, 1, plus 2, 2. And probably I have to do the same, but most probably the dimension is very big and I don't know how to do it. Okay, so it's not very easy to calculate these things. Although conceptually that would be the same. You can say how many maximally entangled states of two qubits I need in order to create this state. Okay, if it's in C3, C3. But already it's very different the world. It's very different. So many other things. You will see it also. So there are very big different things between being bipartite and multipartite, but also between being qubits and not being qubits. Okay? This is why it's also very difficult. So whatever it happens for qubits doesn't have to happen for qubits or qubits or something like that. So why? Because life is fun. I don't know. I live thanks to that. I imagine that it is. Yeah. Yeah, so 1 to 1, that's it. Although, the more that we know, the more we are using qubits, all right? So the first years of quantum information, everything was qubits. Now we know that qubits are very useful for things, and we are starting to learn how to manipulate it, to use it, to calculate entanglement and so on and so forth.
Hi, thank you for the talk. As far as I understand, like these entangled measurements, measures kind of define an ordering. So I can say one state is more entangled than the other. I'd like to know if this ordering is preserved for different measures.
No, doesn't have to be preserved. It's very unpleasant, isn't it? It doesn't have to be necessarily preserved. Okay, so that's the reason that quotations. Okay, so in qubits. Okay, in qubits everything works very well. Okay, so you can have that the measurements are not the same, but they follow. But in other things, not. So you can see, for instance, I don't know, negativity that you use it, for instance, for qubits or things like that. No, they don't have to equal. Non-locality and so on. You can calculate Bell inequalities and see when it violates. And remember that I was saying, for instance, for pure states. And this is not at all a trivial thing, okay? Even if it's 10 o'clock in the morning. It doesn't matter how many multipartite states I have. Bell inequalities are super difficult to calculate because you just make a little bit of probability because you have to have measurements and then you have two parties, two measurements. This is the typical Bell inequality. But if I have 10 parties and I put a measurement that each measurement has 20 outcomes and so on, this is horrible, okay, to calculate. But nevertheless, any pure state, doesn't matter if it's qubits, q3s, q whatever, okay? If it's entangled, it doesn't matter if it's 2, 3, or 25, will violate the Bell inequality. But a mixed state doesn't do that, okay? So you have, and we know mixed states that they are entangled and they don't violate the Bell inequality. And it's clear why, no? Because, well, it's clear, I mean, it's clear. Nothing is clear in these things, but anyway. In this thing that I was writing here, here. Okay, so you see that, okay, this is an extremal point of the quantum state, okay? This is an extremal point of the quantum state, and you have also, and this is another extremal point, okay? And you have, which is a pure state, and you have a Bell inequality, which is violated. But, okay, here you have many states. So this Bell inequality geometrically, it's like if you have a plane, an hyperplane, okay, whatever is in one side violates, whatever is in the other side doesn't violate. So if these guys which are here, okay, doesn't violate this Bell inequality. Maybe they will violate another. And so these things are deep, are connected. But you can have, for instance, that in mixed states, there is a state which doesn't violate any Bell inequality and it's entangled. Or you can have. The only thing that it has to happen is that the state is separable, it has to be zero entanglement, whatever measure you put.
Thank you. You said for 2 qubits, we always can decompose it onto a separable state plus a integrated state. My question is, why it isn't always possible for a more general class of states?
You can do it. This measure,
Yeah, exactly.
this one is PSA, yes.
Ah.
You can do it for any state.
Okay.
But then you can, so here we know it's a singlet for 2 qubits, okay?
Okay.
For higher dimension states, we don't know, but you can always calculate it, and we know operational way of calculating, but it's difficult, but you can do it. But this is always like that. So these are completely general, it's independent of qubits or not, so it's for any mixed state, bipartite.
Beautiful.
Even multipartite, I would say.
Thank you. So if you are considering that your system is evolving in time, you can choose a better method to a system that the entanglement is increasing or decreasing, for example, concurrence or negativity.
Okay, so if my system is evolving on time, of course the entanglement can change, no? And for instance, you can say, can I monitor my state and see of the negatives? Yes, you could do it, okay? Increasing if I don't do anything, just letting evolve will not do it because this is unitary or if it's local, but if it's not local, obviously I can make it increasing and I can calculate the two times. So I can make these measures if you want time dependent, yes, that would have sense, yes.
So if you start with a system entangled, and if you can use the concurrence from beginning for an initial state entangled.
If I sorry, I'm not sure if I understand. I start by my state, which is entangled. It's 2 qubits, I calculate the concurrence. It's different from 0, and then I can see that the concurrence goes to 0. Yes, absolutely.
Okay.
You do it, for instance, no? If you, I have done it. So you want to see if you have a state that it's interacting with something, how it goes until it becomes separable. Yes, absolutely.
Thanks.
I think it was you wanted to ask something or not?
Yeah.
Okay, because I saw you.
Yeah, I just didn't clearly understand the concept of the density matrix rank deficient that you mentioned at the beginning.
So the difference between density matrix and?
Rank deficient.
Okay.
So
So I have a density matrix, okay, so, which is a state. You do the following, imagine, typical thing that you say, I have a density matrix, I want to know if it's entangled or not. I'm going to diagonalize it, okay? And now I will see how are the eigenstates, okay? Well, and I will see if this is entangled or not. First of all, rank deficient means I diagonalize and I have at least one eigenvalue, which is 0. So it doesn't have the full rank, okay? And this is why it's in the facets. But second, if you try to do that, you forget it, okay? Because why? Well, listen, the world, there are many more states which are entangled than not, okay? So if I toss coin and I say, okay, it's going to be entangled or not, it's going to be entangled. Tell you, I mean, entanglement is the most common thing, okay? In this sense. So if I diagonalize my matrix, I will find a basis, and this basis most probably will have entangled states. Although my state maybe is separable. Why? Because there exists another convex combination of other elements in which is separable, and therefore is separable. This is something that it's very difficult when you talk with people which is from condensed matter, because they say, okay, they choose a basis. Which basis is? The basis that diagonalize the Hamiltonian, okay? and it's entangled, yes. And probably there is another basis in which this ground state that you have, it's not entangled. But there it has sense. Why? Because this is what you have in the lab. So when you have a Hamiltonian and you diagonalize this Hamiltonian, that is negative, doesn't matter, okay? And you get the ground state and you say, oh, I have entanglement. And in many cases you have it. That doesn't mean for us, quantum information people, that there doesn't exist another basis in which there is not entanglement. But this other basis you will not be able to realize in the lab, okay? Because it can be super complicated basis, highly entangled or whatever. So it doesn't matter. So when they say that, they are right on their meaning, okay? But not in our meaning, okay? Because if you tell me that, I would say, no, this is not enough. For instance, typical example, more trivial cannot be. The identity, which is highly separable, okay? It's identity here, we don't talk at all. I can write it as a diagonal matrix with bad bases, which are all maximally entangled state. However, this state is separable because I can write it in the computational basis, which is 0, 0, 0, 1, 1, 0, 1, 1. And these obviously are product states. So I have a convex combination of product states is separable. But I can write it as a convex combination of bad states, which are highly entangled. Is the identity entangled? No, it's separable. Okay? So one has to be careful because there are things which are physics, and they are right when they say the ground state of this Hamiltonian is entangled. It's correct. The ground state, it's a fixed basis, and it's not the computational basis at all. It's the basis that diagonalizes Hamiltonian. It's very special, but it's physically relevant.
I want to go back to one of the previous questions. Does Bell non-locality not always imply quantum correlations? Because you were saying about that.
Pure states. Pure states.
Okay.
Pure states, always pure states, if not. A pure state which is entanglement is equivalent to have a violation of Bell inequality, so it's non-local, pure state. Mixed states, not. Why? Because in mixed states you have classical correlations that sometimes they hide your quantum correlations. So although the mixed state is entangled, the classical correlations, because a mixed state, it's a correlation, it's a state which is correlated, okay? They hide and they wash up the non-locality. It's not trivial, it conceptually has some importance, but only pure states.
Thank you for the talk. I wanted to ask if these two questions you had posed, like for the entanglement cost and the entanglement distillation, do they have any geometric motivation?
No, they have an operational motivation. It's not geometric, I cannot put it like that. This is the reason that I'm saying this is operational. Okay, how many singlets I need to get my state asymptotically? So I need to do that, okay? Or I want to have this state for something, I don't know for what, but for something. Okay, and I ask you, can you create me this state? And you will tell me, okay, how many singlets do I need to create it? And I will calculate it and I say that asymptotically I have to have some copies. And the other one, it's also operational. I have created my state in my lab and I'm creating this rho B. And I ask you, can you use it for something? And you say, okay, let me see how many singlets. I want to teleport, how many singlets I can get. Maybe I have rho B, which is very little entangled, and I need 1,000. This is a way, we know how to do it. 1,000 of these states in order that you steal one singlet that you can use for teleportation, okay? And the other ones, it's like that, because the state has little entanglement, but we know how to concentrate this entanglement. These are very nice protocols, which are called purification, distillation, and all these things, in which you know, so they are operational, okay? And they have sense in this meaning.
Thank you.
One final question.
Well, thank you very much for the talk. I have a question about the entanglement cost. You have mentioned that there is a proper distance that has to satisfy such a condition that has to go to zero.
What is a proper distance?
Yes, could you give an insight of the properties, decentralized distance?
So for instance, a distance has to be like the distance in our Euclidean space, okay? So the distance from me to you has to be like the same distance from you to me. If that doesn't happen, it's a strange distance. We have the instances that they don't do that, okay? For instance, Kluback entropy, okay, which is rho log of rho minus rho log of sigma. Okay, they don't fulfill that. What else has to have a distance? The distance has to fulfill the triangular inequality. Okay, so this you have to measure all these things. So when you ask a distance to be a proper distance, you have to ask that it fulfills that it's symmetric, and that it fulfills the triangular inequality. But sometimes in quantum info we use distances which are not good distances in this sense, but they have other things. And the typical thing is this entanglement entropy or Kublack distance, which is not symmetric. But this is what it means.
Okay, well, let's thank the professor again.